Got it. Right.
Okay, so
All right.
welcome everyone, and thanks for coming. So today we are very happy to hear Oleksiy Klurman from the University of Bristol, who's going to speak on automatic semigroups. Please, Oleksiy.
Right. Well, thank you very much for coming and for the invitation to speak. It's a great pleasure, of course, to be virtual in Brazil, and I hope to make it like next summer to in person. Well, it's nice to see, like, of course, like people that I know, and it's also very nice to see. I saw that Jean-Paul Alouche is here, so he got me into automatic business in some way, because after his talk, I know very, very little, and the knowledge is still stable from the time I first heard this from him in IHP. But so what I'm going to be talking about is something about automatic semigroups and really automaticity and how it interacts with multiplicativity. But many of you, I'm sure, in fact, written papers about that and know much more about automaticity than I do. So what I'm going to be talking about is a joint work with Konieczny. But I'm just going to immediately tell you what is actually the main problem that I want to dedicate the talk to. And the main problem is, don't worry if you don't know what automatic means, I will explain what in my view it is. But the problem is the following. It's folklore. We knew it from Jason Bell, but so the problem is the following. I give you a multiplicative semigroup, let's say of natural numbers, commutative semigroup. And I ask you a very simple question: when can it be computed using a finite automata? When is that automatic as a sequence? So the goal of the talk is at the end actually to tell you the answer to this question and maybe a bit of the ideas of how you prove that. But to set up this theme, let me tell you what I mean by automatic sequences and try not to go even to the definition, precise definition immediately. So the examples of such sequences are what is called a period doubling map. So all of those sequences, the way I think about automaticity is those are the sequences which the definition rule is via the digit representations. To me, that's going to be enough. So what I mean by that, the map is -1 to the two-adic valuation of n. So this is one of the examples of the sequence. Another example is the Rudin-Shapiro sequence. So you count number of partners 1, 1 in binary representation, and the parity of this binary representation tells you whether you are 1 or -1. So the two or more sequence, again, you count the number of ones in your binary expansion. If it's odd, gives you 1. If it's even, it gives you 0. So again, so periodic sequences are also automatic. So let me just draw. I will try actually to draw something here, but really the way I see about it, think about automaticity is that the rule, I can understand what the value of the sequence is if I go digit by digit and read it from my number from left to right. So say if I have the well, which one I would take? Well, let's say 2 or more sequence. So if I say the 2 or more sequence, I look at the number of ones in, this is parity of numbers of ones in the digit, in the representation, two-adic representation. So if I have 2 states, it's either even number of ones or odd number of ones. And if I start reading my number n, so say it's starting point, if I read digit by digit from left to right, if I see 1 and I was at this state, then the parity has changed. So I jumped to the new state, which is now the odd number of ones. If I saw at this state, when I saw 0, then I just don't move because now parity of 1 didn't change. And of course, again, if I was at this state, there was an odd number of ones. If I saw 1 again, then I got even number of ones. So I moved the state. And if I saw 0 when I read out, then the digit is 0, then I just remain unchanged. So this is exactly the 2 automaton, which will produce you a 2 or more sequence. So the automatic sequence is really for me, you can, if you don't know what it is, we will not use much of automaticity right now. I'll tell you how to think about that in analytic form. But this is really the way it is. When you have a rule on the digits, this is, and you can tell you the value of the sequence from the digital rule, this is automatic for me. So here is the formal definition. Again, for people who know it, they know it. For people who don't know it, what is the take of it? How to think about that? Well, so we have a n in the q-adic. We have a q-adic expansion or q alphabet. So we think of n as represented in base q. And there is the automaton is we have a finite sets. So before we had like even number of ones or odd number of ones. You can think of more 3 number of ones and so on and so forth. The main important thing, you have finite number of states. And you have a function delta, which tells you when you read digit by digit, where do you jump every time? So this is just this last part. I don't know whether you can see it or not when I'm that, but it just tells you that it reads from left to right and tells you exactly when you see a next digit, where to go. And then finally, so you go around all these states. And finally, how to produce the sequence? Well, for each of the states that you have, finite number, you have a function tau, which tells you the output. So that's it. That is the output. So if you got it, you got it. If you didn't get it, it's okay. It took me a while actually to understand it as well. But really the question that I will be concerned about today is the following. So you can see that automatic sequences, oh, by the way, okay, sorry. So the one way to think about that actually in analytic forms, if you don't want to think about automaton, is the beautiful theorem of Bristol, which tells you that what I told you before and another definition of automatic sequence are exactly equivalent. So the way what Bristol theorem tells you is that the sequence an, say with the values in complex numbers, is Q automatic if the Q kernel is finite. So what is Q kernel? Q kernel is that you take your favorite R, you take your favorite I, and you look at sequences of the form Q to the I n plus R. So the subsequences of indices of the form Q to the I n plus R, where R ranges as a remainder modulo Q to the I. If you look at all these subsequences, and there is only finitely many distinct of them, then such sequence is automatic. So again, you can take, for instance, Qn plus 1, these subsequences. Then you can look at Q squared n plus 2, and so on and so forth. So if among those you have finitely many, then all is good. This is automatic. So of course, if you have a periodic, if you have a periodic mod Q periodic sequence, then there is only finitely many subsequences. And this is easy to see, it's automatic, but it's a bit more. I won't stop on that too much right now again, but that's another way how to think about all these objects. Finite number of subsequences. Okay, so what I told you about is that what is my concern for this talk. The concern of this talk is the following. So automatic sequences, they have additive structure because they're defined in additive way, sometimes. So the natural question in the framework of additive combinatorics of some product phenomena is to ask the question of how do they correlate with multiplicative structure? So how do you measure the correlations really with multiplicative structure? One way to measure this correlation is in the framework of Sarnak conjecture. And Sarnak conjecture tells you, I won't precisely define what that is, but it says that if you take a Möbius function, now our favorite Möbius function, then it's orthogonal to any deterministic bounded sequence, in the sense that there is cancellations in the partial sums. So there has been a lot of things, and some of you in the audience have written papers on the Sarnak conjecture, so I won't tell you what it is. There is a lot of things that have been done. But in the context of what I'm talking about today is the natural question to ask: how is the automatic sequences, so deterministic bounded automatic sequence is produced by the zero entropy dynamical system. So the theorem of Müllner of maybe 6-7 years ago tells you that actually automatic sequences, they do satisfy the Sarnak conjecture. So they decorrelate with Möbius, and that means that they do not have, at least in some way, some multiplicative structure. So that's one way to measure this, how much structure you have. Okay, so the other very sort of natural way to measure how much multiplicative structure you have in there is like, why would you restrict yourself to Möbius function if you can ask the same question about any multiplicative function? So I remind you that multiplicative means f of mn equals to f of m times f of n for m and n co-prime. But you can think of completely multiplicative, let's say, f being completely multiplicative function. And of course, now if I ask the question in this way, so for which general multiplicative function do I decorrelate? I have to put some conditions. Because if you think about that, if A is a periodic function, mod q, and f is a Dirichlet character, they obviously correlate. So I better put some condition on f or perhaps on A if I want to prove something meaningful. And one of the assumption, which is very classical assumption in the ergodic theoretic people which study multiplicative function, is what is called aperiodicity. So what I just said is that I don't want to f to correlate with it to be periodic or in some way. So on each arithmetic progression, I want to have f to have a cancellation. I'm thinking of f as bounded multiplicative function. And in my language, in pretentious language, it means, I won't again define that, but Halash's theorem tells you that this first condition is exactly equivalent to the fact that you are far, the distance between f and the character times n to the it, twisted characters, is infinity for any Dirichlet character chi and for any phase t. So also doesn't matter for those people who know it. I hope that I haven't lost you. So f doesn't look like character times n to the it. So that is the natural thing to rule out periodicity. And an, well, of course, if an is very, very, very constant on very, very long intervals, then an and f might correlate. So you don't want to deal with sequences, automatic sequences, which are not primitive. So basically, you want them not to be too constant on the very large intervals. And any reasonable sequence does satisfy it. So this is example of none. So Lemanchik and Müllner, they really proved that under these two natural conditions, there was nothing special about Möbius, but automatic sequences decorrelate with any multiplicative function of this one. So there is some kind of decorrelation of multiplicative and automaticity. So the question which really motivated whatever I am going to be talking about, at least on my side, is the question of, okay, so what is the most strongest form of correlation between automatic and multiplicative functions? Well, the strongest is when automatic sequence is multiplicative itself. So that would be the first basic question to answer. When can it happen? And that was the problem that started sort of after Jean-Paul's talk in IHP, I started sort of my interest in this question. So classify all automatic sequences which are multiplicative. So that is one of the questions. So you could have arrived to this question from the different perspective of view. What are those multiplicative automatic sequences? And this is, I would just 2 words mention if you're not talking about characteristic 0, but you are talking about other fields. So automaticity is very much connected to the transcendency questions. And the question, if you take in any power series over algebraic closed field K, and you ask the question for which multiplicative functions an, for which multiplicative coefficient does this series algebraic? So this question has been studied in the context of automaticity. And there were, so Beziven and Bell, Bruins and Kunz, they proved that if characteristic is 0, then an is multiplicative and ff is algebraic. If an is multiplicative and f is algebraic, then it can happen only if an is the twist of the Dirichlet character or an is 0. So algebraic power series with multiplicative coefficients are classified over characteristic 0. Okay, so ff should be then periodic. And on the other hand, if you take a FP version of that or FQ version of that, then theorem of Crystal tells you that being algebraic over FQ is the same as being automatic, Q automatic. So this question of what I'm trying to answer is basically this mediate between these questions of Crystal theorem over 0 characteristic and algebraicity and multiplicativity. Okay, so you could have arrived at this question not from the point of Sarnak, but from the point of trying to prove some crystal step theorems. So this is really the question. So okay, and well, I'll tell you a little bit about previous work. Well, up to the point that we got interested in that with Per and then with Jakob. So there has been work, even without formulating what precisely this question of Kunz, there has been work throughout many years. So in this direction, and the work was the following. So Littman and Wolke, they classify periodic multiplicative sequences, which is not difficult. But then there is a very nice theorem of Sarkozy who classified multiplicative sequences that satisfy linear recurrence relations. It's all related to this concept of multiplicativity and automaticity. So then Yazdani, he proved like that a bunch of functions are not automatic, such that mu and phi and sigma and then and so on and so forth. Now, concretely to the example of the question that I'm talking about, I want to understand multiplicative functions that are not automatic. So Schlager-Puchte in 2011, he proved that each automatic completely multiplicative non-vanishing sequence is almost periodic. So if you don't vanish, then you're almost periodic. But really the motivating sort of thing that I would be concerned about is the conjecture actually of Bell, Bruin, and Kunz, who in 2012, they formulated the following, essentially the following conjecture. So each automatic multiplicative sequence must be essentially a Dirichlet character. Maybe something happens on small primes, but on the large primes, so what happens for almost all primes is that you have to be a Dirichlet character. So essentially you're a Dirichlet character times something that is so then there was a bunch of things that related to these works, and there was a result of which classification completely multiplicative. Then Alush Goldmacher, they did something related to the mock characters, which is also in this framework. And then in 2019, well, myself and Per and Lee independently, we proved this conjecture for completely multiplicative functions, and I will show you the proof of that because I really like it. And then a bit later, again, myself and Kuberg and independently Jakob Konieczny proved, well, independent. They both relied on the same input, multiplicative input from the previous paper, but independently and much more combinatorial. We proved the full conjecture. And a year later, Konieczny and Lemanchuk, so we proved that on large primes you are Dirichlet character. And a year later, Konieczny, Lemanchuk, and Müllner, they really understood what happens on the small primes. So beyond them. So their theorem says the following. Their theorem tells that, yeah, let me formulate their theorem. So their theorem says that, well, if I give you automatic sequence, Q automatic, then Q must be power of prime. And it's got the following form, and it's even on the if statement. So you can decompose F as something which depends on the valuation of P in the multiplicative periodic fashion, and something which is multiplicative and periodic, which does not depend on P. So basically you are periodic times something which depends on the valuation of P. So that's it. That is the theorem. Okay.
Excuse me, F is additive or multiplicative?
Multiplicative. But I define it on 0 to be 1 here because it really depends on you.
Okay.
Okay, but I mean, so what I really want to concentrate about, and I like it because this is the part of the, oops. This is the part that we will use eventually in our work with Jakub, is not the final result about multiplicative functions, but about completely multiplicative. And I want to describe to you the proof, because the proof is 1 page, of the following theorem that started out this work after the very nice talk of Jean-Paul in IHPAC. So the theorem that I want to describe to you is an old, by now, theorem of myself and Kuhlberg, and it says that if you have a completely multiplicative function f, which is also Q automatic, then there exists Q such that if n is co-prime to Q, f is a Dirichlet character. So essentially it means that f is a Dirichlet character for every prime, sufficiently large prime. Okay, so this is the theorem I want to prove for you, and then talk about new results or sketch the proof. But this, I hope the statement is clear, because if the statement of this theorem is not clear, then we'll waste right now quite a bit of time. Okay, so if this is clear, let's just try to prove it here and see what does it rely on. So, well, I want, first of all, to make some observations. So if f is completely multiplicative, and since f is automatic, then f must have a finite range, because we said this is finite number of states. So this is the only thing I will use. Okay, so if this is a if I have a finite set of range, then if I take, I claim that f should be either root of unity, f of p on the prime, or it has to be 0. Well, of course, if this is not the case, then I can just take a sequence of 1 power of p, f of p squared, and so on. And for this to be finite, I really need to have that this is a root of unity, okay, or 0. So if I need to only work with the multiplicative functions with the roots of unity in the image or 0. And that motivates you to actually define the set to understand these multiplicative functions or automatic multiplicative functions. Let me look at the 0 set. So let me look at all primes for which f of p is 0. And the entire observation that started all this business of characterization, all works rely on that in some sense, is the following. So here is the simple proposition. Well, that's simple proposition. So if my function f vanishes at infinitely many primes, then I claim that f of p is character for all other primes. Okay, so I claim that then the problem is trivial. So let's do the proof of this in one slide. Boom, doesn't work. So that's the only thing you will need to know about automaticity. So remember what I told you about the kernel, the crystal theorem. Kernel of automatic sequence is finite. What does it mean? It means that there exist two subsequences with I1 and I2, such that the values of f on the first subsequence is the same as the value of on the other subsequence. There exists simply because there is just finite number of subsequences when you range over i's, and even when you range over the r term. But here I just need a very weak statement. So there is finitely many, kernel is finite, then there is a finitely many subsequences, two of them are the same. Okay. Beautiful. Well, okay, so now let me take n to be a multiple of all primes for which I'm 0. And instead of n here, let me evaluate it at this multiple of all primes. Well, then denominator is not 0 because I'm not divisible by any of the prime in P naught. And then this is just 1 because the quotient is 1. It's not 0 quotient. And things that we understood after this talk of Jean-Paul is that actually then the conclusion immediately follows from what Elliott and Kish proved based on this breakthrough of tau. So for people who are here and know about the correlations, this kind of having f to correlate very much on the two progressions, and you can use the machinery then, like which has been developed to refute that. So basically, Elliott and Kish, they proved there are now other proofs like following my work and so on. But really, this is what it says. Elliott and Kish said that such functions must be Dirichlet characters. That's the only way how they correlate. And well, then we realized that probably you can do afterwards. And so now the only thing I need to consider is that when there is infinitely many primes for which I'm 0. So we aim to prove, and for this case, I don't need to prove that I am Dirichlet character. So if I'm infinitely many times 0 for f of p's, then I want to prove that my function is eventually 0. So what I want to prove in this case, that f is eventually 0. Well, if I want to prove that f is eventually 0, I might as well replace f with absolute value of f, and then prove that my range of the function would be just 0 or 1. Because if f was automatic, absolute value of f just changes the output function. It's also automatic. So it's enough to prove that my statement for functions that vanish at infinitely many primes and take values 0 and 1. And now here is the exercise. So suppose that I want to just describe to you what is it really underneath of these theorems. And so suppose I've got like a bunch of primes for which I'm 0. I claim that then there is a progression modulo product of these primes for which my function is all the time 0. So if there is a bunch of primes for which I'm 0, there is a progression on which I'm 0. And this is easy to do by Chinese remainder theorem, forcing first few times to be 0. You can just think about that. I don't want to spend time on this because I want to talk about that, but this is really simple to prove. Okay, so there is a progression. So what is the main idea after? So here is the wishful thinking. So suppose I have some t for my function. Suppose I'm given function f, which vanishes at infinitely many primes, which takes value 0 and 1. And suppose that f of t is 1 for some value t prime, say, and t is a primitive root modulo p1, p2, and pk naught. So recall that f is 0 on this progression, which is modulo p1, p2, pk. So if, say, pi minus 1 if P1 minus 1 and P2 minus 1 and P3 minus 1, say they don't share common factors or share the common, of course they share a common factor too, but suppose that I can find gamma, which is congruent to gamma I modulo Pi minus 1. And such that T to the gamma I is actually R mod Pi. So suppose I can cook up one gamma for which T gives you modulo P1 remainder R, modulo P2 remainder R, modulo PR remainder R. The only thing I need to ensure is that Pi minus 1 and Pj minus 1 do not have common factor except 2, maybe. So if I can do that, then I can take the common gamma. Well, then I immediately get a contradiction, because from one hand side, f of t was 1. And on the other hand side, t to the gamma gives you remainder R mod all of this Pi. So it lands in the bad progression. So the main thing, what I've done here is I said, if T is a primitive root mod P1, mod P2, PR, and Pi minus 1, P2 minus 1, they don't have really much common factor in common, then if I could select this T, then everything would be okay. What is the problem here? Why it is wishful thinking? Well, because the Artin primitive root conjecture says that I don't even know that if I have a fixed number A, then I am primitive root modulo infinitely many primes. So we do not know that if A is not a square for any given A, we don't know whether I'm primitive root modulo infinitely many primes. But there is one of my favorite theorems that I really like this theorem, and this is a replacement for it. It's a beautiful replacement where idea goes back to Gupta and Murthy. They prove it. Actually, even their version would be enough. Keith Brown pushed this theoretic part very nicely, and it says the following, that we don't know that number A is a primitive root modulo infinitely many primes, but we do know that if I give you 3 primes, any 3 primes, then at least one of them is a primitive root modulo infinitely many primes. And the key thing is that there is a caveat here for which the proof works and how we really need it, is that you can insert here, because the proof is still theoretic, you can insert the word here that it's a primitive root modulo infinitely many primes, which lie in the fixed given arithmetic progression. So you can prescribe, if I want to find primes in arithmetic progression to which I am primitive root, you can also do it. It's the same proof. Because it's theoretic. And now I just say that, well, just apply whatever I just said. So Eman, remember that I just cook you up the progression here on the slide. I cook you up the progression for which you have tons of primes by Dirichlet theorem, which are to which you are 0. So you just run this previous argument that I described by choosing T1, T2, T3, the 3 primes on which you are not 1. Module 1 of this T1, T2, T3, if exists, it's a primitive root modulo infinitely many primes in this progression that I just cooked up. And then you get a contradiction. So your wishful thinking becomes really a thing. You need that Pi minus 1 do not have a common factor, but this can be ensured very easily in Chinese remainder. So this is really the gist of it. I don't want to, if you can really fill it up if needed. I hope that makes sense in some way. Okay, so if it does, finally I will talk about something which is new. So this is one-page proof and really not difficult. The other part is also not difficult. The things that I will be talking about is actually quite complicated to make it work. And I will remind you what is that my objective here. So the objective here is that I want to understand which semigroups are can be of natural numbers can be computed using finite automata. So we want to find all sets E which are closed under multiplication, and if I take a sequence AN, which is indicator sequence of this set, I'm asking when is the sequence of 0 ones is Q automatic for some Q. Okay, so I hope that we understand the formulation. And so let's see the examples of such sets. So the example of such sets, so one of the example would be, well, if I didn't know, if I take AN to be automatic and multiplicative, and I look at the level set where AN is 1, now we know that this is periodic sets. But if I take the level set, when I take two numbers M and N, for which AM is 1 and AN is 1, AMN is also 1. So that would be example of the automatic multiplicatively closed subset. So another example would be if I take all N and I remove the powers of 1 prime. Well, the fact that this is closed under multiplication is pretty easy. The fact that this is automatic, it's also pretty easy. You can imagine that the automata is the simple device, and it really can easily check whether you are of the form p to the alpha or you are not of the form p to the alpha just by reading digits. You just read the leftmost digit. So this is clearly automatic. You can easily cook out the automata. The third set, so basically n minus some geometric progression is the example of the multiplicative semigroup, which is automatic. So the third example is well, you take base P representation and you take when the valuations is divisible by a fixed number R, where the digits are only multiples of R, non-zero digits. So clearly this is multiplicatively close, because if you multiply these digits and exponent was divisible by R, everything is divisible by R when you expand it out. The fact that it's automatic set, again, the finite device can easily check going digit by digit if all your exponents are divisible by R or not. As soon as not divisible by R, it gives you the output 0. So again, it's a digit function. So, but it's again something in terms of geometric progressions, some union of geometric progressions of some form with P to the R, B, and N difference. So here is the most annoying part, which is the most annoying part is the following. So that's what destroys structure. So you can take any Q and any set A, which is Q automatic, and then you can take any M and look at the set, which is the multiple M times your any automatic set, plus take the union with M squared, multiples of M squared. Since you don't see on the board what I write, I won't try to write it. But so if you multiply two numbers of this form, then you are divisible by M squared. So you are certainly closed under multiplication. And you can check that you are actually also an automatic. Well, I mean, it's because this part is automatic and this part is just multiples of M squared. So it's an automatic set. So if you are, and how would you prove the structure if you want to understand? Because A can be anything. So it's a bit complicated. But what is to take from the fourth example is that you don't want to have all your members of automatic set to be a multiple of the same number. Naturally, you don't have such thing. So here is one of the, I won't state you really the main theorem because it's a bit too technical. But what I will try to state, I will show that essentially these are the only examples that you have. So the theorem, the general theorem is that this is the only one example. So here is an example of a new result. So the example is the following. Suppose P is a prime. Then what I can do is I can partition P into sets. So E0 is the set of all co-prime elements to P. E1, this is, I factor out P, and E1 is co-prime to P. So it's according to the valuation of P. So if I just partition everything according to valuation of P. So the theorem, one of the theorems, says the following. So suppose E is the K automatic semigroup. And let's suppose that we are not in the fourth part. So suppose that E contains an infinite pairwise co-prime subset. I mean, it's not a strong assumption. If it doesn't, then you are one can prove characterization anyways, but it's a bit more complicated. So suppose E contains an infinite pairwise co-prime subset. Then the theorem says that essentially whatever can happen is only what I described before. So if K is a power of prime, then each of the set EI, this is a periodic set minus the geometric progression. And actually the geometric progression with the multiple, with a p to the alpha step. So the only way it can happen is exactly what I described, periodic set minus geometric progression. And if K has a two prime factors, then you don't even need to split it into exponents of P. You know that you are minus the union of geometric progressions. And this is essentially if and only if. I mean, I don't give you precise formulation of everything, but this is the gist of it. If I don't have infinite co-prime subset, you also can do it, but it's a bit more complicated to state, but you also have a characterization then. So this is really the main theorem. And I don't know how much time do I usually have in here. So I started at 5:05, but I don't know how long is your...
Yeah, usually it runs for 55 minutes.
55, so I have about like, okay, for 55 is the talk, so until 6 or something, like until 5:55.
Yes.
Okay, so then I will tell you a little bit about the proof. I will tell you the main thing about this proof. So the proof, unlike in the previous slide, the proof is quite involved, but the idea is quite simple. So we don't have this multiplicativity result that we can rely on Tao's work. So I would want to construct a multiplicative structure to which I could apply such theorems, or approximately multiplicative structure. And this is going to be the idea. So here I don't have multiplicative structure. I have just a semigroup. But let's try to build up, and I want to show you what is this, where is the multiplicative structure comes into play. And to this thing, I want to, sort of with waving hands. So if I'm going to do any kind of number theory on this automatic things, there is one thing. The first thing you want to understand two things. The first, whether you have a density, whether you're working with dense or sparse sequences. And the second thing is how dense you are in arithmetic progressions. So those are sort of two things if you want to try to do some analytic number theory on the object. So the first one is quite a well-known thing, and maybe it's even in Jean-Paul's book with Shalit. This, if you take an automatic set, then it doesn't necessarily has a density. It doesn't necessarily have a density, but it does have a logarithmic density. So this is the well-known fact, and that's what I will operate. So remember, my goal right now is to show you what is this multiplicative object to which I will try to prove automaticity and reduce it to my previous results. Although it takes pages. So this is what it says. We have a density, logarithmic density. And the second thing, which is not that well known, at least we couldn't locate it in the statement that we need. So if you have an automatic sequence, then essentially you are dense in arithmetic progression. So this is what this thing, logarithmically dense in arithmetic progression. So what I mean by that, so let's just try to understand this. Well, somewhat quickly, but so what I mean by that is that if I intersect, imagine there exists some discriminant, finite number of primes. So as soon, maybe just look at the conclusion of that. So whenever I look at whenever Q and K are co-prime, so when I am not Q is not a divisor of K, then if I look at the density of how my set E intersect arithmetic progression, then it scales naturally. So Q prime, you can think of Q as being co-prime to the delta. So delta is a fine product of prime. So if Q and delta are co-prime, then Q prime is 1. And it just said that for most of the large Q, what happens is that the density is exactly 1 over Q. Or rather, the density is exactly the same as it's supposed to be. It's exactly the same as the density of the set. So let me just say one more time. If I have E in particular, what I will apply it to is the following. If I have my set E and I look at the multiples of Q, which is Q is say large prime, if I divide if I find in my set E all elements that are divisible by Q, and I divide by Q, and I look at the new set, then the density of this new set is exactly the same as the density of the previous set. So that's what it says. So 1 over Q, it scales as it should. For Q, which are not divisible by small primes. So what I mean by that is that here is the key observation which guides entire argument. So if E is an K automatic semigroup, if it's just semigroup, and suppose that Q belongs to E, and Q is co-prime to this discriminant that I had before, then I claim that when I take E and I divide it by Q, then the density is roughly the same then set as E up to the measure 0, up to density 0. So this is the key thing. There is something when I divide by Q by the elements, it doesn't change the set much. And the reason is, as I told you before, the left-hand side here, it contains E because I'm semigroup. So if I take the element and divide it, it contains E. And on the other hand, the density of left-hand side is the same as density of E by the previous lemma. So it contains E and the density is the same. So it means that the symmetric difference is within density 0. So, and that motivates you the definition, which is actually, it has nothing to do with automaticity, has nothing to do with the even semigroup. The definition of the invariant set, and actually the entire theorems are actually about they're much more general than what I said, have nothing to do with automaticity, they have something to do with the semigroups. So what you look at is for any set E, you look at the invariant set of E. Those are those Q for which when you divide E by Q, if you take multiples of Q, when you divide by them, that it's not too much different from your initial set. And for semigroup, you know that this set is already rich because E is already inside the invariant set E, but it might have more. And the ref E, this is, well, say number 12 may be an invariant subset, but 3 and 4 might not be. So I also, ref A is those are all divisors of this invariant set. So this is, again, invariant E, this is those multiples that remain your set invariant, and ref E, those are divisors of all these numbers. So, and the key here, the map that will eventually be, or rather modification of this map will be automatic and multiplicative, is the following. So this has nothing to do with being, it's true, this statement is true for any set, subset of integers. For any subset, no multiplicativity, no automaticity. So if I give you E, this is any set, then there exists a 0 group. So 0 group, this is group, take a union with 0. So before it's like, say, roots of unity, take a union with 0, and so on and so forth. So, or a field without addition. So, and epimorphism. So pi is a multiplicative map. It's a map which respects multiplicativity, such that it satisfies the following. So the image, pre-image of 1 is actually my invariant set. Entire group is the pre-image is my ref E. So the key point is that anything non-trivial is happening on ref E, on the divisors of my invariant set.
And this pi is compatible with the density, with multiplication. So if pi of q is pi of q prime, then they act on E pretty much the same way. So I won't keep you too long, and I would just like try to, maybe I'll just give you this quick example. If you didn't follow like what this thing does, is that, so you could take E1 to be 1 mod cube, say, the set, and E star to be integers co-prime to some q. Then what is invariant of E1? Well, those, if you take n is 1 mod q, invariants of E, those q prime, for which when you divide numbers, you get the same subset roughly. So of course, this is the same as E1, because if you want to get the same subset from 1 mod q, then you better divide by 1 mod q. And what is the divisors of all these numbers? Well, E star, of course, because any number which is 1 mod q is divisible by some number which is, or any number which is co-prime to q divides some number which is of the form 1 mod q. And this pi in this is just the multiplication. So the group is just z mod q z star, and the multiplication and the map pi is just a mod q. So this is nothing really complicated. So I'll stop here, but I will tell you one word. So this was the last slide actually. So I will not comment on that, but what is your wish for specialists? Your wishful thinking is to prove that pi e is automatic. And we don't know how to prove it. So everything that I said before is not applied. What is the problem? The problem is in the last part, where you would be able to prove that this is automatic if you didn't have equalities up to measure 0. Then you would be able to prove it. So, but here, because you have equalities up to measure 0, the definition of invariant set has to be modified. Has to be modified that you have actually exact equalities and on every connected component of the automatic. Then you can go it through, but it's much more technically demanded. But this is the idea. Some modification of P of E will be multiplicative and automatic, and from here you would be able to prove the characterization again after some work. I'll stop here and thank you for your attention.
Thank you, Oleksiy. I'll open up for questions, and also
yeah, for many
comments.
people. Well,
I thought someone was saying something.
yeah, sorry. It's not my usual thing, as you probably were hoping to, or some people were hoping to hear something about multiplicative functions and really about analytic number theory. On that side, this is more on the side, of course. So there is not much analytic number theory in this group. But nevertheless, I think it's quite, I quite like this part. My experience with automaticity is rather limited.
Yeah,
To one paper.
it's probably less limited than mine and maybe some people.
Well, now thanks to Jakub. Thanks to Jakub, he knows much more.
If there's no immediate question, maybe I'll stop recording, then we can chat a bit.